Morning. So I think this is an exciting time right now for applications of many of the really impressive results and hardware that we saw a little bit earlier in this session this morning, the advances in methods that we saw this morning and throughout the last day and a half. And one of the important areas for application of machine learning is in manufacturing and operations. And indeed, there is a machine intelligence transformation in progress. It's going with stuttering steps, and I'm going to try to talk through both why the transformation is happening, what we're learning, we and industry are learning as we try to make this transformation, and what some of the challenges and approaches might be. Again, every 10 years or so, there is a big paradigm shift in manufacturing and operations. In the 80s, it was really the shift to lean manufacturing, just-in-time kinds of concepts, et cetera. In the 2000s, there was another transformation, which was from local sourcing to globalization. And now we're really in the middle of the digitization shift from programmatic control of our operations and factories to applied machine intelligence. And what's driving this? Well, at least three things. One is the impressive improvement in sensor technology. We have much more data coming in, as well as the ability to communicate it. And that data is highly structured and highly, if done well, highly available. And then, of course, we also have the dramatic growth both in the computational resources and in the algorithmic methods. And indeed, the opportunities here are enormous, sort of scary numbers from McKinsey and others about the possible improvements of efficiency in operations and manufacturing in the $1 trillion kind of range. So we've got this very rich landscape out there. We've got a plethora of data, and it's very interesting data coming from manufacturing and operations. It may be very hierarchical. It's not all image data, right? It may have to do with factories and equipment and processes within the factory and parts within the factory. It's highly spatial, right? We have replication. We have multiple tools. We have multiple assemblies. We have multiple parts. And it's highly temporal. Often these are temporal data streams that we have. We also have this gigantic, rich set of machine learning methods. And one of my messages here will be it's a lot more rich landscape out there for machine learning methods than you might think from the public press, which is all focused on deep learning and convolutional neural network, sort of for image processing. Okay, so part of our interesting challenge here is how do we map these methods onto manufacturing and operations problems? Okay, and so as we've been collaborating with industry, we see many companies sort of in the pilot stage, trying out a few of these machine learning methods. But it's a confusing and complicated landscape, and the playbook doesn't exist for how do I use, which is the right method to use. So what I'm going to try to do here is share with you a few use cases from our collaboration in areas of process optimization, process control, yield prediction enhancement, defect inspection, anomaly detection, spatial variation modeling, these sorts of applications that arise in manufacturing and operations. And you'll get a sense then of some of the potential benefits from appropriately applying machine learning approaches to these kinds of problems. However, I will also be highlighting to you a number of the recurrent challenges when you try to take sort of off-the-shelf machine learning approaches and use those in operations and management. And these problems include things like often we have a small data problem. We have a class imbalance problem, not always big data. We have concept or model drift, and I'll show you examples to explain many of these. We have very complex time dynamics. These multivariate time sensor signals are quite complex. And we also would like to incorporate domain and the domain knowledge and the underlying physical or engineering knowledge and not throw that away and hope that some neural network reinvents that. We'd like to find ways to take advantage of what we already know. And the last point is we also do depend on explainability, interpretability, and trust, as Alex Madre was talking about in the last talk. So I'll give a few examples of different methods. Certainly, deep neural networks are an important tool, and I'll show you examples of those in manufacturing. But we also find when we go and interact with industry that a number of those other methods in that large taxonomy that I showed you are especially valuable. It's not all about deep learning. Simple things like clustering to start to understand groupings of your data can be extremely valuable. We've also found that decision tree-based models, random forest or boosted decision trees, maybe more than 50% of the time when we try them out on manufacturing data compared to neural network approaches, the decision trees do better. So it's very interesting application domain dependencies on some of these kinds of data. And then there are also other methods, and I'll show examples of a Bayesian or Gaussian process kind of model, probabilistic frameworks that are not deep neural network, but that also enable us to assert what our uncertainty is, and also to incorporate some of the domain knowledge that we may have. Okay, so I'm going to go through some of those use cases and examples. One of the first, and I'll map these onto this taxonomy. By the way, this taxonomy is not comprehensive. Just to guide you through, it includes things like supervised learning, where you have labels and are trying to build a model that produces, say, a prediction of a value or a label, cat, dog, et cetera, but also at the top, unsupervised learning kinds of approaches, where you're trying to discover patterns in the data that maybe give you insight into what's happening. And then a whole rich area, and again, some examples I'll show in the middle, of what I call semi-supervised learning, where you're actually trying to guide or optimize both the model construction, but also perhaps optimize your manufacturing or other process. So one quick example, and this is a neural network example, is an optimal run-by-run control algorithm. And the basic idea here is this is your classic sort of feedback control kind of notion, but with a model in the middle, right? So I've got the plant up here at the top, and what I've got is some simple model, a dynamic model of what the output should be as a function of whatever my knob settings are, my controls on that particular process. And what we observe is some deviation, perhaps, from what we expected, and I can use that to update the model and then solve the model backwards to figure out what the next recipe or control decision would be. One of the problems with these dynamic models is how quickly do I update that model? How do I adapt it based on the information that I'm getting while running? And in fact, that optimal weights question within this particular algorithm is an important question. And so what we actually did is not use a neural network for the model. In fact, the model is a very simple linear model. But we needed a complex mapping of what some of the input characteristics were, say from the noise or the drift in the process, to what the best weights are in order for the algorithm to adapt itself. And we used a neural network there and got good results in terms of quick response, but also sort of optimal response. Now, one of the fun things about this is from one of our papers at an International Manufacturing Technology Symposium in October 1996. So we've been doing this for a while, but what's changed? Computational capability, sensor data, again, a much richer set of the methods. But now is the time when this transformation can start happening. Let me show you another more recent example. This is work with SanDisk, a memory chip manufacturer. And this is about yield prediction and enhancement. In this case, it does not use deep learning. It uses random forests and decision tree kinds of models to make classifications about whether a chip is going to be good or not. But we also found we needed to do online learning. So let me set this problem up for you. What we are getting are incoming chips, incoming wafers from the wafer manufacturer, and an engineering test program is run on about 1,000 different electrical parameters. And that e-test program was designed by the engineering team to say whether that chip is going to be good or not when packaged. But lurking inside of what are supposed to be all good blue chips are a few die, a few chips, that turn out not to be good once they're run through the entire packaging to a multi-chip stack packaged product, say a solid-state disk drive, okay? And so these are high-end products that if all of those chips work in the output, I can sell that as an SSD. And if I've got some bad chips in there, it becomes a thumb drive and is not very valuable, right? So there's a high value to making a good decision about whether these chips are good or bad. And that's why the e-test program was invested in. Our question was, can we add to that e-test program and add a classifier before the packaging that tries to look at subtle things that are still, subtle correlations, as we heard, that are lurking in the incoming die in order to make a little bit better of a decision about which are the good die that you should package in the high-end product. And it turned out the classifiers that we used were random forest classifiers. I need to give you a little bit of a picture here, sort of a mini tutorial on how we characterize a good classifier. What we want to do for any chip is make a decision about whether it's a good chip, we've got a true positive decision rate, or if it's a bad chip. We've also got a false positive rate. And obviously, we'd want to make the right decision as often as possible with as few false alarms or bad decisions as possible. And so there is a curve that characterizes the classifier, the ROC curve, that depending on what threshold I make on how big the signal is from the classifier, I decide whether it's a good or bad chip. So any better classifier goes kind of toward that corner of perfect decisions without erroneous decisions. Okay, so we wanted to build a good classifier for this particular problem, and we ran into quickly two problems. One is we have an imbalanced classification problem. We actually have lots of data. We had 3 months of all of the chip packaging data from SanDisk on this particular product. But it turns out they have pretty high yield, and the number of examples of bad chips are actually pretty small. So imagine I've got a 96% yield already. A classifier that is 96% accurate, has an accuracy of 96%, is pretty trivial. Tell me what that classifier is. What's the decision? Pass it. You're 96% accurate, right? But it's useless as a classifier. It's not giving me any additional information. It's declaring every chip to be good, and 96% of the time it's right. So in fact, a 96% accurate classifier, sort of in the machine learning literature, you go, wow, that's great. But it's not great for the purpose in our manufacturing problem, right? And the problem is, I really need to focus in on those little 4% bad cases. So we've used some approaches from the machine learning community around undersampling and boosting in order to account better for those small data, really valuable data cases. A second problem, and this is one that we've seen occur again and again in manufacturing, is I may build a model. I might spend 2 or 3 months building a machine learning model. And then I start to apply it. And that model is good on day 1. It's good on day 2. Day 3, it's not so good. It decays with time. Over a week or 2, the model loses its effectiveness. What's going on? Many of those subtle correlations are changing with time. So we often face this problem of how do we keep our model up to date? And the approach I'll show you here is online and incremental learning to address that problem. So we built a combined classifier that tries to do this problem. First off, the boosting and undersampling find that we can do better than the, just declare everything to be good Here's the curve, the ROC curve, and superimposed on this are some contours that you may have a little trouble seeing, but they show the yield gain in packaged product depending on what decision I make, whether I throw away chips and lose yield or package only good chips. And we can see that I can get about 2 or 3% improvement in a chip stack of 4 memory chip product, or even more yield improvement if I have 8 chips being packaged together. So our boosting approaches do give some benefit there. But in fact, what we did see is that concept drift really does exist. If I took that 3 months of data and segmented and just built or trained a classifier on some subset, the blue subset of data in one particular 3-week period, and then test it on the sort of held out test data, that's this purple curve. And I get a very nice ROC classifier. It gives me some yield gain. But if I look at the next test set, sort of the next 3 weeks batch, it's not quite so good. And I look 3 weeks later, again, the classifier accuracy decreases, it decays. Okay, so what's the approach? Well, as good engineers, feedback is a great approach, right? I need to continue to adapt and update that model. So what we'd like to do is keep taking new measurements, getting new information at the end of the line about which chips really were packaged or not, and use that to continue to update and maintain and improve that classifier. And indeed, when we do that, there's some methods here for deciding how to weight older and newer data. We've got an incremental learning approach that enables us to try to maintain that classifier. And when we do that, we get 2 benefits. One is it's maintained well over time, but in fact, compared to the batch classifier, it does even better. So it actually is able to pay attention to the salient, the most recent data that actually matters a lot more. And indeed, we get a little bit more of a yield boost. Okay, so that was an example related to yield improvement with an online learning classifier. I do want to show you at least one deep learning example, because these are exciting methods. And a very common challenge in manufacturing is defect inspection and classification, right? But we also, again, face a problem of often not having a lot of data in a manufacturing and operations environment, certainly compared to the amount of data that's out there on the entire internet. So we may have a tire inspection goal, a tire inspection problem where we have images and we're looking for visual nonconformities, say in the tire tread, based on some laser triangulation data. And we'd like a predictive model that both tells us the probability of there being a nonconformity, and then using some of the gradient methods or saliency methods to localize or identify where that data is. But in this problem, in this collaboration, we only had about 1,000 different images. And even a small handful of those were only the defect images. So what do? How do we train a network? And the basic idea was, let's borrow and steal from the larger machine learning community that have already trained networks for image classification problems. And in particular here, we looked at the Inception v3 model, which is trained on ImageNet data. So millions of data points on classic classification problems. And as we heard earlier, the early stages of that pre-trained network are really feature extractors. And we want to use those and essentially replace the later stages for our classification problem. And so the student in this case did that, sort of kept about the first 8 or 9 layers of the Inception v3 model and the weights of that, and then built a new classification layer for the tread defect inspection problem. And in fact, that worked very nicely. Good results there, good ability to detect defects as well as to localize those defects. So this is a great example of transfer learning, where we can try to take what has been learned in one problem and now apply it with benefit to a related problem. So that was a deep learning example. But I want to, again, make the point that many of the other methods that populate this universe of machine learning are highly interesting and highly applicable to different domains, in particular manufacturing and operations domains. And so I want to show you an example related to spatial variation modeling. In many processes, including semiconductor manufacturing, we have wafers that have spatial extent, and we would like to be able to predict and build models both of the spatial performance, but also the process dependencies. So this is an example that uses Bayesian methods, okay, where we can build in some a priori knowledge and then does reinforcement learning or optimization based on those models. So this particular example is looking at wafer scale variation in a particular deposition process. And you can see from a 300 millimeter round wafer, a scan across the diameter of that wafer, I may have plus or minus 10 to 20% variation in this particular manufacturing process, right? So how do we model that? Well, what's coming from complex interactions of the tool, but also depends strongly on the process recipe. So both equipment parameters and equipment configuration, but also how I design or optimize my process. There's a lot of knowledge that has gone into the design of these tools and this equipment, and one of our challenges was to mix and use that physical and empirical knowledge, but also to try to optimize or minimize that variation. And the particular approach that we found attractive here were Gaussian process models with Bayesian learning. What's a Gaussian process model? The basic idea is there's a different kind of correlation that relates to the similarity between data points depending on a distance metric between those data points. So you might think of this x as a spatial location. That x could also be a process parameter. And I've got measurement points that nail down what the response is, my f of x for that. But I also have lack of information. I have uncertainty bounds or confidence intervals in places I haven't looked yet, right? So one thing that's very attractive about these Bayesian approaches or Gaussian process approaches is I have some notion of confidence. I know where I'm sure, but I also know where I'm not sure. Another attractive element is that the parameters here can be both spatial and process-oriented at the same time, okay? So given that, we'd also like to mesh that with engineering knowledge. And in particular here, we had access to a physical model that takes some of those equipment configuration parameters and is able to produce sort of predictions of some quasi-physical other parameters in the equipment. But we were able to use that as sort of a physically motivated feature extractor. Gives us those X parameters that tell us what's similar to each other or not. What are important features for this particular process? And based on that, we're able to produce a pretty good predictor, a pretty good model that says as a function of both space and process parameters what the prediction of the output would be. So using that, then we can go into a Bayesian optimization or reinforcement learning approach. Again, taking advantage of enormous developments in the machine learning community that focus on how to best optimize but also learn simultaneously. Because what I'd like to do is minimize, say, find the best operating point for that particular manufacturing process. But right now, I say at the beginning, I only have a limited amount of test data or trained data, and I'm not sure where the minimum is. In fact, because of those confidence intervals, I might look around and say, maybe it's over here, maybe it's over here. What I'd like to do is either explore more in order to get more information and get more confidence in my model, or I might like to exploit. I already have enough confidence, go ahead and pick your optimal operating point. And so there's a very nice set of formalisms for designing the acquisition function that helps guide this trade-off between exploitation and exploration. and with a small number of additional data collection points. You move towards the optimum, but you're also learning along the way. And so that's what we were able to do here in this particular deposition process. We optimized down to about plus or minus 5% non-uniformity in this particular example. So I want to show you one last set of examples that give you a little bit of a sense on time series data. So I've shown you some spatial, I've shown you some yield, I've shown you some image examples. But one of the very common goals in manufacturing is to do anomaly detection. Is my process still working normally or not? And here I'll return again to a variant of neural network approaches, recurrent neural networks, but also show you basic things like clustering to start to understand patterns in your data can be very helpful. And this is another semiconductor manufacturing example. We have a particular plasma etcher. It has a bunch of different sensor signals on it, maybe about 31 parameters. I've shown you one parameter here. It's an endpoint optical detector parameter. And for each wafer run cycle, you get a curve that looks something like this. And I've superimposed some number, I think 10, 12 different runs. This is a normal run. These are some abnormal runs. You can start to see this does not look like the other. So we'd like to have a way to both decide, well, what's the group of good ones and bad ones? And then also, can I make predictions based on good ones so that I can detect bad runs? So here's a little sort of toy example. This is, I think, just a subset here of something like 10 or 12 of these cycles. So this is one wafer run, this is another, and so on. This has been carefully selected where it turns out the expert knows, right now we don't quite know, that this is a good run, good run, good run. This is an anomalous run. These are highly anomalous. Not only did they peak out, but they've got other glitches in them. So some clustering approaches can start to look at the data, just those time series data, treat the entire time series as a feature set, and identify groupings. Can say which cycles looked similar to each other in one way, looked similar to each other in another way, or looked similar in a third way. That turns out to be really useful because then you can also now go with a few examples and show an expert in the fab and say, here's a representative example of this cluster. Is it a good run or not? And all of a sudden, inexpensively, you've been able to label. It's sort of a semi-supervised approach. You've labeled all of your data by imputing what the label is for all of those elements in the cluster. Okay, so that clustering step can be highly advantageous. By the way, there's other kinds of clustering approaches that are also really useful, like a hierarchical clustering that would say I've got all of my data and I can split that into two, what looks like a non-anomalous group and an anomalous group. And within that, there's two different kinds of variations. And within that, I can even keep dividing down. And that might be very useful for diagnostic kinds of purposes. What kind of failure or anomaly are we seeing? So once I've got good data, now I can go and train a model that says, for the good data, this is the kind of time series I expect to see. So we used here and tried out just regular feed-forward neural networks, recurrent neural networks, and compared it to classic time series kinds of approaches. And indeed, one is able to build and test a very good model that predicts what a normal cycle is supposed to look like. And then one can use that in anomaly detection. When you start to see big deviations between your prediction and what you expect, now you can signal some kind of an alarm. And indeed, what we found was the basic neural network approaches, both the feed-forward and LSTM, worked well. Interestingly, the classic autoregressive integrated moving average statistical approaches failed miserably in this problem. So we did find that the degrees of freedom that come with neural network approaches were very advantageous for this particular problem. And indeed, what we found here is that in basic situations, you get an awful lot of leverage out of basic ideas of clustering and then training with relatively straightforward neural network models. But there's a number of additional opportunities and challenges remaining, including taking advantage of other data, multivariate data that we have, not having to train a model for every individual recipe or every individual tool. We'd like to take advantage again of that transfer learning idea to be able to share our learning across multiple instances in our manufacturing environment. So one of the key intermediate points here is it's a really exciting time in manufacturing and operations. We've got, again, rich data and many manufacturing and operations problems, but we don't quite know how to deploy them. Right? We're starting to build some experience, both individually in our companies, but also in the research community, about how to map to and what are the appropriate methods to try to use to solve some of these problems. But it's a community challenge. It's an industry challenge. We're only partway through this transformation. And so one of the things that we've done here at MIT is recognize out of these point-wise collaborations there's a need and an opportunity for a little bit of a group effort. And for that purpose, we've, under the Quest for Intelligence banner, we're putting together MIMO, an activity across campus on machine intelligence for manufacturing and operations. And the basic mission here is to help industrial competitiveness. We want to accelerate the deployment of these methods and understand what works, what doesn't, what can wisely be used, what can ethically be used in manufacturing and operations in these methods. We have 3 key activities that we're undertaking. One area is in education, really training both students here at MIT, but also seeking to facilitate training of those already in industry, whether through executive education, new case studies, or best practices. What is the playbook? And get that out there for people to use. A second activity is around the transformation. We're really trying to build that structured approach, those best practices, and do this not just on the campus, but we found that this field work, trying these methods out in industry in collaboration with our partners, has been crucial to understand both what the challenges and problems are. And so we want this to be a highly interactive, industrial, collaborative activity. And toward that end, one of our first activities in the innovation space to advance the state of the art of machine intelligence solutions and their determination is not only doing the research, but also try to get a sense of what the state of the art is out there in industry. And so there's 3 opportunities for you to participate in MIMO. One is fund some research. There's a cohort of faculty across campus that are really interested in these kinds of problems. So we have opportunities for sponsored research. We are working with ILP and the Quest in mid-March, March 17th. We're putting together a day-long workshop, a day-long symposium on operationalizing your enterprise AI strategy around data readiness and data-driven decision-making. So we hope you might come back and participate in that. And a third is an initial activity with some of our existing partners. I think it's over 25 leading companies that we've surveyed. What is the state of art, state of readiness, and state of application of machine intelligence in their current manufacturing and operations? How far along are they in that journey? And so there's opportunity to both get access to some of those results if you participate in that survey. And so to learn more, feel free to contact me. One of my close collaborators is Professor Recep Levy in the Sloan School of Management. We're working together as faculty with Bruce Lawler, who's the managing director of MIT MIMO. He's standing up over here if you want to try to find him also for follow-up questions later as well. So with that, thank you.
Thank you very much. We've got time for a couple of questions. Okay, since we don't seem to have any audience takers, I'll ask a question. So in terms of your interaction with industry, it seems like you've got well over 2 decades of experience. How have those challenges changed over time, and how has the receptivity of the corporate collaborators changed to the methods that you've used?
Yeah, it's very interesting. So I would say the earliest work in trying out machine learning kinds of things was before that first AI winter, or that last AI winter, where we sort of hit some roadblocks in trying to use the machine learning approaches, as did the rest of the community, and there was a bit of a burst of bubble for a while. And so on the machine learning front, we sort of said, well, we're going to call our methods statistical methods. And so we pursued those for about 10 or 15 years. And now it's many of the same methods. They are enriched by this larger taxonomy. But now all of those statistical methods are, again, machine learning methods. So I think there's always been receptivity to advanced mathematical approaches that are informed by engineering and business judgment throughout all of that time. But often they've been more narrowly focused. What I think is exciting now is there's really an opportunity to generalize some of those. So it used to be a very narrowly focused method that could solve that point problem. And we'd get some benefits and great student results and a paper and some benefits for the company. But now I think we're at a different place where we can start to write that playbook. We can start to say, what are the general approaches?
So, awesome talk. When it comes to a lot of machine learning methods, a lot of times the conclusions that you derive are dependent on the quality of your data, especially when you're talking with industrial sensors with like failure modes and things that can go wrong. What are the benchmarks that you use to determine like just how good your data is before you send it through whatever algorithm?
Yes, absolutely. And just, I guess the slides have gone back. I was trying to go back one slide because I think actually data quality and the processes, business processes and other engineering processes around the data, very good, are actually one of the important things we want to talk about at this upcoming March workshop. It's around data readiness and data decision driven decision making. And so there are some basic approaches that are pretty clear. We start to know, and we heard a little bit from Alex, for example, you have to integrate some methods, even in sensor signals that you were talking about, for outlier detection before you use or train on those sensors. So there's some canonical approaches that we can kind of build in that achieve some quality in the data or screen out some of the data. But then there's the much bigger question about, well, how do you structure the data? What do you use a data lake? How do you integrate disparate data sources that in order to sort of achieve the scale are really big challenges right now. If you narrow in on one point process, you can start to employ engineering, machine learning, and statistical approaches. But you've put your finger on data has to come first. In fact, many of our collaborations with industry have been at the point in which they've invested massively in new sensors and in new data collection and maybe even data aggregation. And they're looking at this data and saying, I should be getting more value out of this data. So, in fact, getting the data is one problem, but then machine learning to also take advantage of the data is an associated problem.
One question on the manufacturing floor, when you're doing mass production of things, very often it's absolutely imperative to protect the customer from exposures of a certain type of defects. It's not so much as to increase the overall yield, but to protect the customer. To do that, would you suggest some obvious means to train the AI package, like excessively train the AI package with the failures or with just the passers? Are there obvious approaches?
They're not always so obvious, but they're really valuable. So one of the examples is, in fact, think carefully about the business use, protection of your customers, failure detection, and build the model appropriately for that. So worry about, and maybe you even, as you're hinting at, overweight the failure examples to make sure that you can detect those. And in fact, that's what the undersampling or oversampling does. But the second one, and I want to highlight your approach there, is there's the whole inference. Once you've built a model, the decision making that one does. And that's where it's not paid as much attention to until you have your application problem. But now you have to sort of look at the relative costs of a true detection, relative cost of a false alarm. It may be very costly to allow a defect through. And so in your decision-making process, you want to, not just your model building, but in your inference from that, take that into account for what decision you make. In fact, that's what will change your decision point on that ROC curve for a classifier based on those relative costs. So great insight there.